Many times we are asked, what is the best antenna for my situation? My basic response is always, tell me more. There is no one-size-fits-all solution for LTE antenna applications. It is not wise to just pick the highest gain and be done. And I'll explain why as we go on. My name is Keith McKechnie. I'm a solutions engineer with USAT. Basically, I've been hanging around wired and wireless communication systems for a few decades now. When we have a client come to us for help in determining a successful LTE antenna solution, we typically ask these questions. Do you have any signal at all on a cell phone with a carrier of your choice at the target location? That's the starting point. And if they have full bars, we would usually go down one path. If low or no bars, we would need to investigate further, with things like how far is the closest cell tower? Is there more than one cell tower within range? What does the terrain look like between the location and the cell towers? And what are the physical constraints for mounting antennas at your location? To dig into the complete solution, I'm going to break the discussion down to these specific points. The first is the type of antenna to deploy. There are many, but I want to specifically focus on rural applications here. To narrow it down, I'm going to focus on 4 different types. The first is a multi-band Omni antenna, used for applications that are located within reasonable cellular coverage but need to locate the antennas outside or some distance away from the cellular device. The further away the better. The coax cable needs to be to offset the loss. We'll take a deeper dive into coax cable a little bit later. Side note here, this antenna is now available in MIMO, which is 2 antennas in one, and LTE does require 2 antennas for proper reliable operation. The next antenna is a panel antenna. This particular panel antenna is called the X-Pol 2 and is a high-gain cross-polarized MIMO antenna. Panel antennas are directional. They are used for applications that need some additional gain because of location, or they have space constraints for antennas, or they're budget conscious. They know that LTE requires 2 antennas for proper operation, but only want to pay for 1. It's the lowest cost MIMO solution that we have. The next one is called a log periodic dipole array, LPDA for short. This is a wide frequency band antenna as it covers all the cellular bands in the United States. It is used for applications on the edge of cellular connectivity or applications on the edge of MIMO Effectivity. A similar antenna, but one step back in performance, is a Yagi antenna. Not full wide band coverage and not as high of a gain. The last antenna I'm going to talk about is rarely used, but it is worth mentioning in the context of rural applications. It is used when you are on the extreme edge of cellular connectivity with one specific tower. There's some drawbacks though. It requires precision aiming and great physical stability, and it does not have consistent performance on all LTE bands. I discussed a few different types of antennas. Next, I'm going to talk about the radiation pattern of antennas. Antenna design means everything when you need to connect reliably in a remote location. A couple of key points here. Don't look just at the peak gain spec. Look at the gain values over the entire frequency span of LTE. And look at the quality of the 3-dimensional antenna gain pattern over that frequency. Now some cool visuals. What we are seeing here is a 3D simulated radiation pattern of a directional antenna. The antenna itself is located in the center where the X, Y, and Z lines meet. It shows the relative gain in all directions, and the dark red represents the highest gain and is the direction where the antenna is pointing. Typically on some spec sheets you will see only 2 slices of this 3D pattern. The azimuth is the top view and shows the relative gain as if you were looking down onto the top of the antenna. The elevation is the side view gain pattern as if you were looking at the side of the antenna. Looking now at both the top and side views, the next parameter I want to talk about is beam width. The center of the beam is defined where the power of the signal is at its peak. In the RF world, for every 3 dB of drop, you're losing half the power. To get the beam width specification, you measure the angle off each side of the center where the gain drops off 3 dB. The total is the actual beam width. Notice the beam width is a complete arc. It is not the plus and minus beam width. Also notice that the gain is not maintained evenly over that beam width path. On this slide, we're going to look at how the design beam width influences the gain. There's a lot of math and fundamental equations as to how beam width and gain relate to each other. Looking at the Omni antenna on the left, what you want is that it radiates equally well in all directions. Looking at the top view, in general they all do. Here's 3 different Omni antennas with a top view of increasing gain patterns. Now looking at the side view of those same antennas, you'll see how the gain increase happens and what you're giving up in exchange for the gain. The side view of the radiation pattern shows a marked difference in the antennas with different gain specs. In order to get the highest gain from an Omni, the radiation pattern is focused narrowly in the horizontal direction. Not so good if you're in a valley or a hill, but great if the terrain is somewhat flat. Remember I asked the terrain question in the beginning? It's not always about the highest gain. The medium and lower gain antennas have a pattern that is better if the cell towers are located significantly upward or downward in elevation from your site in a hilly area. For directional antennas on the right, as the design of the antenna produces higher and higher gains, you are focusing the radiation pattern from both the top and the side to produce maximum results. The downside of this is for a very high gain directional antenna, you need to take more time to dial in the physical position of the antenna to the cell tower for maximum results. However, when you do, you'll achieve results that are not possible any other way. Another downside is that you may become more dependent on your connection with just that one cell tower. If that tower goes down, the gain pattern may not be that great, to where the signals of the backup cell tower are coming from. So it's always a trade-off. As LTE technology has progressed with more and more LTE bands on different frequencies, it is imperative that any antenna solution has good performance on all those LTE bands. The reason the antenna solution must cover all the LTE frequency bands is because you have no control on which LTE band your device operates on. That band is negotiated between your device and the carrier, and many times the carrier will change it on the fly when they need to balance their traffic. Here is a snapshot of the common frequencies that the carriers use for LTE. We have found that an antenna company called Poynting covers these bands very well with their products, and are now being deployed large scale in oil and gas and the utility space. When I spoke about antenna radiation patterns, they were static radiation patterns. What is important to note is that radiation patterns change with different frequency as well. This is where a lot of antenna manufacturers play a lot of games in specmanship. They often will quote the highest peak gain regardless of the frequency at which it occurs. And many times this point may even be outside of any cellular band. A good vendor should fully expose their gain specs over the full frequency range that the antennas could be used in. In addition to gain, the actual radiation pattern of the antenna changes dependent upon frequency. In the case of an Omni, it's not always a ball shape as you see here that shrinks and expands with different frequencies. And you will see visuals of that coming up. In this example, the gain at 2100 MHz is 7 dBi, and at 2400 MHz it is 13 dBi. This is a big delta in such a short distance in frequency, and if the system is supposed to operate over both frequencies, you may have an issue in edge coverage situations. This confuses people to no end many times. Up to now, we talked about the variations of the pattern and the gain with direction, and we talked about the variation of gain with frequency. We also have the problem of variation of pattern over frequency. On the top left side, we have an ideal patterns of directional antennas, and hopefully the pattern would remain consistent over frequency. On the right side, we have a poorly designed antenna where at some key frequencies it has a null in the gain at specific directions from the antenna, yet a higher gain off to the side. Surprisingly, it could be technically okay to quote the peak gain at one of those side lobes, which would give the false impression that the gain is good in all directions across all frequencies. A nice high gain Omni is shown on the lower left. You want it to radiate well towards the horizon. A lower gain Omni is shown in the middle where it radiates well in all directions, including elevated directions, like in a hilly area. Quite often, you may find an antenna that performs as shown on the lower right, which is a disaster of an antenna. It is failing in terms of both its omnidirectionality and elevation pattern. The interesting thing is that technically, one could quote a higher gain with a disaster on the right than the ideal one in the middle. This is simply because one of those lobes or isotopes are peaking out in specific directions, maybe even up in the sky at the high level, yet in many other directions it is much lower in gain. Up in the sky where there's no cell tower, for instance. Why would that be of interest to someone? Physics would dictate that if I wanted to radiate in all directions, that the middle one would have to quote a lower gain when one on the right, because of all those hot spots in obscure directions that are impractical. And on top of that, those hot spots vary with frequency as well. For the common antennas, here are the typical gain over frequency specifications. A closer look at the LPDA, we see a peak in the low bands, then it dips below 8 dBi between 1100 MHz and 1600 MHz. But that's okay since there are no LTE bands in that frequency range. It is then solid out to 3 GHz. For the X-Pole 2 panel antenna, we see good consistency throughout all the LTE frequency bands. For the omnidirectional antenna, it ranges between 4 to 6 dBi in the low bands and 6 to 8 dBi in the higher frequency bands. Frankly, I'm not too worried in the lower frequency bands since those frequencies penetrate better anyway, and they're easier for receivers to receive compared to the higher frequencies. This allows for more forgiving specs for antennas in the lower bands, so to me, it is well balanced. With LTE, you are required to have 2 antennas. This is also known as MIMO operation. MIMO stands for multiple input, multiple output. Technically what it does is exploits the multiple paths a signal takes from a tower to end-user equipment to increase the link capacity for a larger volume of data. If the quality of the signal is high enough, then multiple independent streams of data is negotiated and exchanged with the device, creating much higher throughput. Using 2 antennas is now not just for increasing throughput using MIMO, it is now required for reliable operation. The reason is because Verizon and other carriers have been slowly converting their systems from transmission mode 2 to transmission mode 4. We have had some customers get away with running on 1 antenna for some time. However, a year or so ago, one of our utility customers had over 100 systems go down overnight. The cause was determined to be a change to TM4 from Verizon. They added a second antenna to each of their systems and then the problem was solved. Real quick. Here is a technical diagram showing 2 independent data streams represented by blue and red on the far left. Each stream is received by each antenna at the receiver on the right at slightly different times. The result is digitally processed by the DSP on the right, and the streams are separated back out on the far right. Antenna polarization also comes into play with MIMO operation. Antenna polarization, in its simplistic form, is just the mounting angle of the antenna. What is shown on the right here is a peak inside one of those panel antennas on cell towers. There are multiple pairs of cross-polarized antennas, each one representing a separate channel within an LTE band. The signals from these antennas are launched in a cross-polarized manner with each other, one at plus 45 degrees and one at minus 45 degrees. Now let's talk about MIMO effectivity a little bit here. The modem CQI, or channel quality indicator, determines if the signal conditions are such that MIMO can work effectively. If it can, it sends out an indication to the tower to transmit 2 independent streams of data, or the MIMO. When the CQI at the modem is too low, then the same data stream is sent out on both antennas. This negotiation of MIMO happens really fast. Here is an example of a mobile driving down the road in a fringe area for MIMO. It shows by color going in and out of MIMO connectivity. Since the signals are launched in a cross-polarized manner from the tower, plus 45 and minus 45 degrees, the most optimal antenna system for the modem is a cross-polarized antenna system. Shown here is our X-Pole 2, which has matching polarization inside to achieve maximum MIMO effectivity. Another example shown here is two of our LPDA antennas mounted on a special bracket that converts them into a cross-polarized solution. A better solution for LPDAs is to mount them on separate poles at least 10 feet apart. But if your application is constrained by space and/or does not have very high throughput requirements, then this solution is best as it matches the antenna polarization that is launched in the cell tower. A little side note here, so the level of the channel quality indicator also controls other things besides MIMO going on or off. It basically determines how many bits can be stuffed into a time slot, which greatly affects what your actual throughput will be. Now that the antennas are selected, the next decision is what type of coax to use. The longer the length, the more you need to focus on the characteristics and quality of the coax. This chart shows some common types of coax cable and the signal loss at the end of a 40-foot length. Notice that the loss is greater at the higher frequencies. When LTE first came out, it was mostly under 1 gigahertz, so the loss in the coax was just not much of an issue at that time. In the past, the most popular coax cable was RG58. Notice how bad the loss is in the higher frequency bands for RG58. Do not use RG58, and if it is in current installations you're looking to upgrade, rip it out. Interesting enough, the HD 195 coax is close to the same diameter of RG58, just a much better design. When looking at the gain specs of an antenna, know that it is at the base of the antenna, not at the end of the cable where it is spec'd, even if the antenna includes a cable. This slide shows gain values in both the upper and lower bands for 3 different antennas. Now after adding 16.4 feet of coax, LMR 400 for the LPDA and the Omni, and for the X-Pole 2, HD 195 coax is included and attached. Notice how the gain drops in both the upper and lower frequency bands. Now for a full apples to apples comparison, we could cut off the HD 195 on the X-Pole 2 and add in LMR 400, and these are the results. On this slide I show all three solutions using HD 195 versus LMR 400. You can see that the difference is 1 to 2 dB, but that is just 16 feet. The numbers are much more dramatic when you approach 50 feet. We generally suggest to use LMR 400 for any application over 25 feet, and for rural applications you should consider using LMR 400 for any length of coax. The last part of the total solution I want to touch on briefly is lightning, or better described, static surge protection. So many years ago I was active in amateur radio, and I had a large large vertical antenna in my backyard, and there was a storm in the area, and typically what I would do is disconnect the coax connector cable and connector from my radio. During the storm I was in the room and I heard this tick, tick, tick sound, every few seconds. And I think, what the heck, where is that coming from? And I traced it down to the actual connector of the antenna laying on the floor. There was an arc, there was a spark that was jumping from the tip to the sleeve of the coax cable. And so the story is, these antennas will collect static electricity under a storm just being in the area, and this static electricity has to be arrested to ground in order to protect your electronics in your system. The basic component looks like this. It is a 50 ohm device that passes DC to 6 gigahertz with SMA connectors on each side. It is a sealed gas chamber that essentially reacts to voltage spikes above 90 volts and quickly shorts them to ground. This slide shows optimal configuration using LPDAs on the edge of coverage in a rural setting, and you can see where the lightning arresters fit in. With MIMO optimization, you space the antennas at least 10 feet apart, and optionally you can match the plus 45 and minus 45 degree polarization with a special bracket. Although with the antennas spaced 10 feet apart, the polarization is much less important. Definitely use LMR 400 coax to your demarcation point, which is where you enter a building or a box if it is an outdoor application. At that point, you install the lightning arresters with ground wires as short as possible to a solid ground such as a ground rod, then short jumpers from the arresters to your cell gateway or router. A little closer look at the mounting options for the LPDA. As mentioned, the optimal solution is to mount them 10 or more feet apart on separate poles. However, many applications are space constrained, so we have a bracket that will cross-polarize the antennas. Here, the two orientations you can mount the bracket on a pole with. There's also another bracket available that converts the LPDA to horizontal polarization. In cases where you still have one pole, but you have room to spread them out a little bit, and you may want to consider that option as well. Here is a closer look at the model number of the cross-polarization bracket. And finally, a closer look at the model number of the horizontal mounting bracket. This converts the antenna polarization from vertical to horizontal. I touched on earlier the antenna type that could be considered an extreme edge of connectivity cases, and that would be the parabolic antenna. Parabolic antennas are best used in point-to-point applications and rarely used for cellular. The main reason is that the peak gain over frequency varies a lot. So if you have connection on band 4, then the carrier tries to move you to band 13, it may drop the connection. In addition, the beamwidth is so narrow, you will have great difficulty in aiming it, and you will need to keep it stable. You should really only consider these as a last resort, and you will need 2 of them, of course, for LTE. Poynting is our manufacturing partner of choice for rural applications. As LTE expanded its frequency bands, we knew we had to find a quality partner. We found that Poynting provided better gain specs across all cellular frequencies and supported the emerging bands. Poynting uses high-quality material and puts their products through rigorous testing. Poynting designs their product to stand up to adverse environmental conditions. I can tell you that in the past 3+ years we have provided several thousand Poynting antennas to our customers, and not only 2 of them came back as bad, and with each of them they were suspicious of external physical damage. Poynting's quality specs are available upon request. Just a quick review of the main Poynting antennas presented. Here we have the Omni 292 V2. And notice the V2. Poynting has a continuous performance and design improvement process, so they do not shy away from introducing improved models from time to time. Just a quick review of the main Poynting antennas presented. Here we have the Omni 292 V2. And notice the V2. Poynting has a continuous performance and design improvement process, so they do not shy away from introducing improved models from time to time. It comes with an L bracket and U-bolts for pole mounting. Here is the X-Pole 2. It is a MIMO antenna, which means it is 2 antennas in one package. It comes with 5 meters of twin HD 195 coax cable permanently attached as well. And finally, the LPDA, which is the highest performing antenna from Poynting. Before I go, I want to briefly touch on 5G. The understanding of the term 5G has changed a bit in recent years. It's not going to replace 4G LTE like 4G did 2G and 3G. Now 5G has broadened so much that it is used to refer to anything broadband wireless with higher speeds. Recently, organizations have been talking about 2 very different technologies and lumping them into 5G. One's called Sub-6 and the other is called millimeter wave with massive MIMO. Millimeter wave 5G is totally different technology and completely out of scope with these types of antennas we discussed. Sub-6 5G means anything under 6 GHz. The CBRS 3.5 GHz and the LAA 5.5 GHz bands are what's being referred to here. You may have already seen cellular antennas branded as 5G and spec'd at 600 MHz to 6 GHz. And that's great, but anytime you have to expand the frequency coverage in a single antenna design, you have to compromise on the performance. These are very complicated structures inside these packages, and the level of design expertise to pull it off is intense. The higher the frequency you go, the less penetration ability and the less distance the wave will travel at a given power. Now, this is physics. We're not able to change that. The sub-6 5G frequencies from 3.5 gigahertz to 6 gigahertz will not be in play for rural edge connectivity, and which is why this presentation we didn't focus on them. As you may know, 5G is mainly focused for urban areas. Thank you very much for your time today. Again, I'm Keith McKechnie with USAT, and we are the distributor for pointing antennas in the United States. Please contact us. We're happy to discuss your application and help you get going.